My name is Nola Charles, and this is my lab for Faraday's Law for Physics 2212. To introduce this lab, the overall purpose was to find the average time for a bar magnet to fall through a tube of an aluminum foil, both computationally and experimentally. The main fundamental principles that we used were Faraday's law, the Biot-Savart law, Newton's third law, and then Newton's second law. And then the main results were for the experimental model, it took 0.708 seconds, and for the computational model, it took 0.497 seconds. And then the main physics idea formulas are shown on the right, where we use Faraday's law to calculate the current induced on each ring by the falling magnet, the Biot-Savart law to compute the force exerted on each current-carrying ring by the falling magnet, and then we use the Newton's third law, which is the one on the bottom, to calculate the force exerted on the falling magnet by the whole tube of current-carrying rings. And then we use Newton's second law to rewrite the position and velocity updating formulas within our computational models. For the initial conditions, the ones I used for the computational model are on the left. For the systems, I set it to be the bar and the aluminum tube, where the surroundings were everything else. Then we also assumed that there was no drag or air resistance, as long as no other magnetic or electric forces, external electric forces. And then the thicknesses of the tubes, as well as the radiuses and the lengths, are shown on the right. For the experimental model, we did 5 different trials where we recorded the time it would take the bar magnet to fall through the aluminum tube, and this was my average time. And then for the checkpoint, for the reason we can't use a ferrous tube, it would be because it would reduce the magnetic field, reducing the flux, and then thus reducing the induced current. And then what would happen to the magnet? How does this compare to a magnet following in free space? It just followed much, much slower with the induced current present. Here was the computational model. We started by creating a function to calculate the magnetic field of the bar magnet, and then we moved on to create a function to calculate the magnetic flux. And then we moved into doing our simulation loop, which we would use to work on the prediction and visualizations. This is just part 2 of that. Then this was the results for the computational model. And then for interpreting the simulation, we first had to look at what the direction of the currents would be. So for the red, I got counterclockwise using the right-hand rule, and then for the blue, I got clockwise also using the right-hand rule. And then what happens to the dynamics of the system when you flip the magnet around, it would be the exact same. It just would have different inverted properties. The physical properties would be the exact same as far as speed and magnitude. And then how does the total time in the tube of your real-world system compare to that of the computational system? Well, the computational system is much faster because it doesn't account for drag or air resistance or any external electric or magnetic fields. So to make it more accurate, we just account for these. And then what does the shape of the velocity versus time plot tell you? Well, when the slope is 0, it tells us that the magnitude of the magnetic force and the magnitude of the gravitational force must be equal. And then for human error, the biggest one would be that my magnetic dipole moment from lab 2 was too small, so it wouldn't show up properly on the computational model. So to fix this, I scaled it by a factor of 2. And then I also assumed that there would be no drag or air resistance, which could be room for error, as well as human error in the stopwatch. For what if, for this question, since current is equal to EMF over resistance, if the resistance was close to 0, the EMF would be a lot larger, meaning that a greater induced current would occur, meaning that it would look very, very, very slow falling, or if the resistance was close enough to 0, it wouldn't be moving at all. For this what-if question, the magnitude of the induced current would be significantly decreased, as it would be harder for the path of the induced current to properly spiral down the tube without exiting through the slots. Thank you.